Hello class, and welcome to part 2 of chapter 1. We're covering petroleum geology. It's some of the things that we're going to go over. We're going to go over a little more detail than we did in part 1. Now, a lot of this will be review, but these things are very important. So the more we go over them, the more that you'll understand them. And it's just going to help you even that much better understand the rest of the book and the rest of the course. So let's get started. Now, geology is earth science dealing with the origin of the earth and the history of the earth and the physical structure of the earth. And also your ability to understand this is going to help you to understand most of the course. Scientists try to answer questions like, how is the earth? So we went over class. We say that the earth is 4.55 billion years old, according to scientists. Where did it come from? It was a bunch of dust and smoke floating out in the atmosphere or out in space, and gravity pulled it all together and made the earth. And it's made of all kind of minerals and rocks and different things. So the examination of the fossil records come by looking at earthquakes and volcanoes and drifting continents and the relationship of past events to present events. Now, geologists are concerned with rocks that contain oil and gas, and they want to find the rocks that contain enough oil and gas to make it worth their while to drill for it. So they want to be able to not only find those minerals or petrochemicals, but they want to be able to extract them from the ground. Now, two primary jobs of the geologist is to reconstruct the history by looking at rocks in different strata, or you'll see those lines in rocks, and then determine if it's worth going after. An oil reservoir is not a large underground lake of oil. Some terms that people use are oil pool, petroleum reservoir, water drive, but it is a rock formation that contains oil and gas within the rock itself. And if you think about a sponge, that will help you understand a little better how it is. Now, to determine how much oil and gas it contains, they look at how broad it is, how shallow it is, how narrow it is, how deep it is. And we have some fields in East Texas that it's only 5 to 10 feet thick, but it's thousands of acres big. And then also there's a field in Holland that's only about 5 acres big, but it goes down some 85 feet thick. The most important rock that scientists look for, geologists look for, is shale. Shale is a rock that contains a lot of oil and gas. And if you think about it, today we're using hydraulic fracturing to crack that shale to release the petrochemicals or the oil and gas that's below the surface. So the most sought after is shale. That's where you'll find the most oil and gas. As we said before, the Earth, according to scientists, is 4.55 billion years old. And gravity is the prime mover of the Earth. Heavy metal, iron, sank to the core. And the mantle surrounds the core, made up of lighter minerals. And then the crust is a thin shell of rock on top that's floating on top of the mantle. Now, when you have these plates, these thin shells of rock floating, you think about it somewhat like an M&M that's been cracked, or maybe even an egg that's been cracked, and the outside part that's cracked floats on top of the part that's under the bottom. Now, when these plates move, it's called plate tectonics, and that's how the Earth gets its shape. Okay, you have the crust that's at the top, and then you have the mantle, and then you have the outer core, and then you have the inner core. It's not to scale, but we'll look at it a little bit more in depth in just a second. Now, certain fossils on opposite sides of the ocean are similar, and coastlines match in many parts of the continents. So if you take, let's look at this. Hold on, here we go. Now, if you look at how South America and Africa and India and all of these different continents, they look like they would fit together if you had a puzzle, if they were pieces of a puzzle. But if you look at this animal right here, what is that? I don't know what it is, but whatever it was only found right here in this part of Africa and this part of South America. And if these parts were to fit back together, those fossils would be found here. The same with this type of animal. Their remains were found right here. Australia, these plants were only found in this blue area. So when you look at these different parts of where you found these animals, they don't swim, so it would be difficult for them to have been there if the land masses were not connected. Now, there's a picture in your book that shows you this, so this is a little hard to see, but look in your book at this picture. Now, when the Earth, around the time it began, scientists believe that the mass of the Earth or the land was all one piece. And then as millions of years went by, the land masses started to separate. These plates, different plates of continents, started to drift apart. And then they started drifting apart even further and even further. And now this is the present day look of how the different continents or the crust started moving, which is called plate tectonics. And even now, those plates are still moving. That's how we get earthquakes and different land masses moving and going up and down in the ocean. So, that's a better picture. That's how everything looks today. But if you look at this South America, it could possibly have fit right here, Australia up in here. So it's pretty cool. That's how it was a long time ago when it first began, one landmass. Now, oceanic crust is thin. It's about 5 to 7 miles, and it's made up of heavier types of rock. I don't know whether it's heavier because it's compressed or just because it's just made of heavier things. So, but oceanic crust, thin and it's heavier, 5 to 7 miles. Then you have continental crust, which is thicker, 10 to 30 miles, and it's comprised of lighter type rocks, and that's why it floats like icebergs on a sea of heavier rock. So it goes to the top. Now, this is very important. This is how plate tectonics work. It's like a conveyor belt. So when you look at the different layers, we talked about the inner core being solid and the outer core being a liquid, and then the mantle being a solid, and then the crust is a solid. But the mantle is solid, but it's more like a thick, gooey something because the rocks are melted, but they're cooling off as compared to how compared to the temperature they were when they were in the core. So as this what is it called, magma, as this magma comes to the surface, it comes to the surface and it starts to ooze out and starts to harden, and then it contributes to the part of the crust where it comes up and makes a slab. And when that slab starts to move, it moves along, and as it cools off and some of it is heavier, it tends to dip down and starts to melt, and then it comes back around, and then it cools off, and it does it over and over. And that's where you get your movement. That's really part of the rock cycle too. We'll look at that in just a few. The sea floor is spreading. We got deep ridges along different crests under the sea, and pressure from lava coming to the surface spreads the plates apart. Subduction, where the plates are in collision, complete the conveyor belt. So subduction is when the plate dives down, like I guess you can say a submarine. But subduction is where the plates dive and go around in a circle to get on that conveyor. Now, these are different subduction zones. Here's one right here, and here's one right here where the lava is, or the magma is coming up, turning the lava and then pushing the plates apart. And then the plates hit, and then they go back under the ground, and then they come back up. So that's a part of the conveyor belt in subduction. Here's another example: oceanic crust being thinner, but it's being heavier. And then when you have the convergence, the magma coming up, it forms this crust and pushes it, and then that crust, which is heavier, goes down and it melts and it comes back up, and it goes around and it melts and it comes back up. This is some of the same type of thing. When the magma comes up, it pushes the plates this way and pushes the plates that way. And that's what makes these ridges. Now, there are three basic structures that occur when rocks deform due to tectonic movement. And deep formations are high enough temperature that the pressure makes them behave like plastic, and they can bend instead of fracturing. So when you have the rocks melting and they bend instead of breaking, you get warps and you get folds. And when the pressure gets too high on them and the rock doesn't bend, it breaks and causes a fault. You think of a fault being more like a crack in the ground. Now, warps occur when broad areas of the crust rise or fall without even breaking, so they just bend. It's a tilting effect, or it's called dipping. So you can see it's dipping from the left to the right. Folds are like rock. You'll see them, they have crumbled or buckled in waves. You can see that picture, figure 1-7 on page 5. The most common structures in mountain ranges are folds. They go up, and then they're called arches, and then if they go down, they're called troughs or synclines. The upward arches are called anticlines. A dome is a short anticline dipping in all directions. So if you have, it's high in the middle, but it goes downward all around in a circle, then that is a dome. The opposite of a dome is a basin. A basin is a short syncline dipping downward in all directions. And a basin is the point or the part of the formation that a lot of geologists look for. They look for basins, and that's where they find a lot of oil or gas. Anticlines and synclines. As you see, this anticline is dipping down, and then it's making an arch. And then the syncline, it goes the opposite direction, making like a, not really a bowl, but opposite of this wave. It waves down. A dome, it goes down on all sides. And then this is a salt dome. And a lot of times when these rock formations were formed, they formed in the ocean, so they end up getting a lot of salt in them. Here's a basin. A basin is the opposite of a dome. It's a depression that's going up on all sides or coming down from all sides, but it's lower in the middle than it is all around the edges. Faults. Rocks near the surface can break and move, and that causes faults. Faults are like cracks. The two halves can move side to side, or they can go over each other, or up and down to each other, up and down, normal or reverse, or a combination of them. Now, when we look at this, this is a fault, and then when this is the normal part, or the ground, the part that did not move, the part that falls down. This is a dip slip. This is a slip, not dip slip. And then this is a reverse dip slip, when you have the normal piece, or the normal elevation stays the same, and then one piece cracks and then goes up. So that's called a reverse. And then also you'll have a crack, and then one part goes over the other one. That's an overthrust. And then you have a strike slip, and that's when the two parts stay on the same level, but they end up sliding in relation to each other. And then this is like a weird one. So I don't know. I don't even really know how to describe that one. If somebody can figure out how to describe that one, let me know. Surface features. Faults can produce surface features like a graben, which is a long narrow block of crust with the two faults on the side, and then the middle part falls down lower than the parts on the sides. But then you have a horst that is similar to that, but it's a block that comes out of the middle and it rises up. Now these faults affect the location of oil and gas accumulations, because as the oil and gas moves around, it may go to an impermeable rock, and then it has to stop there. This is a graben. You have two fault lines, and then the part in the middle falls down. This is a horst, when you have the normal part, but the part in the middle breaks and comes up. Geologic formations are defined by the fossil record. So when they look at the different fossil records, they can tell how the formation is, whether it dropped or whether it came up, or what kind of rock it is. So they can look at those formations and the fossil records. Now turn your head to the side and then look at this one. This is the Mesozoic period, 200 million years ago. That is the period that we look mostly to see, to find oil and gas. So let's look at it next. Now the Cenozoic, that period has quite a bit of oil and gas, or hydrocarbons, but mostly the Mesozoic period. 53% of the oil that's found was formed in that period. And then you have 10% of it that was formed before that. Interesting. Different kinds of rock contain different minerals and different physical properties, and they're formed in different ways. Now there are three major types of rock, and this is very important. You got igneous rock, you got sedimentary rock, and metamorphic rock. I think somebody was trying to describe to me metamorphic rock as being a rock that's changing. That's cool. I can go with that. Here we go. Let's look at some of that. Magma, which is molten rock that's deep underground. And lava is the magma when it comes to the surface. So it's really the same thing, but one just under the ground and the other one is above the ground. When neither of them is cool, when either of them cool to form a solid rock, it's an igneous rock. So igneous rock is the first rock that comes from magma or lava. When they cool, they turn into igneous rock, and they're very hard. You got granite and you got basalt. Now, formed in horizontal layers or strata, when you look at different mountain ranges or pictures, you'll see stripes that go along the mountains. Well, those are the strata. And sediment can consist of eroded particles of older rocks of all three types, and then minerals that precipitate from water, that come from water. In both cases, water is critical to the creation of sedimentary rock. So you have to have water to make limestone, sandstone, shale, and clay. And which one did we say was the most that they look for to find petrochemicals? Yep, that would be shale. Band of one type of rock is called a formation. So when you have the different strata, depend on how thick it is, that's called a formation. So if you have a strata or a line of clay, that's a formation. You have a stripe or a line of shale, that's a formation. But all of those are sedimentary rocks, and they come from eroded particles. Any of these three types of rock buried deep underground, whether it's subjected to high temperature and heat, the physical and chemical changes occur, which produce new rock. And those are metamorphic rocks. Those are the rocks that come from the sediment rock or any other type that gets heated and a lot of pressure on it, and it changes. So when you have rock that changes, the chemical change and the physical change, you have metamorphic rock. So here's the rock life cycle. I suggest that you memorize this and be able to draw it. You can draw these lines if you want, but for sure you need to know all around the edges. So let's get started with the magma. The magma is a liquid and it's under the surface. And as it comes up, it changes and turns into what type of rock or what type of substance. It is called lava when it reaches the surface. So it starts to cool and crystallize, and then it turns into igneous rock. So magma goes directly to igneous rock at this point. So then the igneous rock starts to be weathered and starts eroding. It starts crunching up into little bitty pieces, and then it turns into sedimentary rock. Well, sediments. It has sediments, and then those sediments start to compact and start cementing themselves together, and then they turn into sedimentary rock. The sedimentary rock then goes and has heat and pressure applied to it, and it dips down. It goes down with heat and pressure. Then it turns into metamorphic rock or rock that's changing. It starts to heat up, melt, get pressure, and it turns back into magma, and the process starts all over again. Now you can get different rock that skips steps, but really, if you just think about it, it's a big circle. The life cycle of a rock, very important. Now, the organic theory comes and says, it states that sediments contain organic material or things that were once living. That's what the sediments in the organic theory. So they're saying that oil and gas came from things that were living. Pressure and temperature from overlying rock strata and converted into petroleum. So these sediments that were made of animals and plants got compacted into the strata and then were converted into petroleum. In organic theory, that organic matter is not required, original formation of the planet. So it did not have to come from things that were living. So that's one theory of how the oil and gas got here. Hydrogen plus carbon equals a hydrocarbon. Petroleum must accumulate in order for it to be worth going after. So migration, rock must allow for movement of the petroleum. To allow for movement of the petroleum, it has to have porosity and it has to have permeability. And it has to have a physical boundary, something that's going to stop it and make it pool in one location, and that's a trap. Now, porosity is holes in the rock. Permeability is the ability of the oil and gas to go from one pore to another pore. You can have pores in the rock and have oil and gas in it, but if you don't have permeability, then you won't be able to get the oil and gas out. And this is sedimentary basin. Most of the time, that's where they find the oil and the gas in a basin. A basin has a lot of potential for finding oil and gas. Porosity, tiny pores in the rock which can contain hydrocarbons or other fluids. Now, if porosity is not sufficient, they won't go after it. Anything above 10% porosity, they usually think about going to get it. Depends on how big the formation is. So above 10%, they may go get it. Permeability is when the pores are connected. If the pores aren't connected, you can't get the oil and gas out unless you do something like frack the site. And the unit of measurement is a Darcy. We probably, in millidarcies, we probably won't do any figuring with that right now. All right, porosity. If you look at the rocks, they have pores in them. These are the pores, and this is the rock part with the little fossils in there. And these pores contain hydrocarbons. Now, for you to be able to get this out of the rock, the pores have to be connected and provide a path. So this is a path for the oil or the gas to flow, and it has to be permeable. If the rock is not permeable, then you're not going to be able to justify going after the oil or gas. Now, petroleum cannot be allowed to migrate indefinitely. If it does, then you won't have any accumulation. So you need a trap. A trap is an arrangement of rock layers that contain this accumulation of hydrocarbons. Now, if it's impermeable, the layer that's impermeable, that's the layer that would trap the hydrocarbons. And the different types of traps are grouped by features, structural and stratigraphic. I think you got anticlinal traps, you got fault traps, you got plug traps. Plug trap is like a dome. A fault trap is a crack, and then an anticline is like a warp, basically. Here's an anticline type trap, and this rock is keeping it from going. You have gas on the top because it's lighter. Then you have oil, which is the next lightest, and then you have water. So the oil is floating on top of the water. This is a structural anticline trap. And then here's another type of trap, the fault trap. You see where the ground slid and the oil was going, but it had to stop because it reached an impermeable piece of rock. If you look at this, this is a typical salt dome where it's trapping oil and gas here. This is water, and then it's got gas and oil and water in that formation. Now, stratigraphic traps or strata are non-porous formations sealing off the top edge of a reservoir bed. And so they can happen just about any way, and they are usually a combination of the traps. Somewhat like this. No conformity is over here, it's over there. Sometimes it may be hard to find this oil and gas because it doesn't follow any kind of rules. Here's another type. And if you look at this structural and the stratigraphic has it split up, and the structural is holding it all usually in one spot. Now, where they find the oil and gas, 75% of the oil and gas that they find in different structures, anticlines. Those are good structures to look at. Fluid, liquids, or gases, any substance that will flow. Three primary fluids that make up a reservoir is natural gas, petroleum, and water, which is mostly salt water. And this is usually how a formation is made up. It's got the gas on the top, and then it has the oil, and then it has water. Sedimentary, here we go. We need to look at this. Sedimentary formations usually happen in or near salt water. Now, connate water is the water that's trapped within the pores. And free water is able to move through depending on the porosity. And so sometimes you have water on the bottom and you have water on the edge. This is bottom water, where you have the water under the bottom of the oil. The oil is floating on top of the water. And then here it is with this formation right here. You'll have water around the edges. Now here is the connate water. It's around the granules or the sediment that makes up the rock. And so that water got in that formation when the rock was formed, and that water won't come out, but it does take up space. You can get the oil out, but that water is going to stay because it's chemically combined or chemically bonded to these different sedimentary granules. Connate water takes up some space within the pores, and it's called wetting water. Permeability is critical for the recovery of this oil, and then the type of dry mechanism will dictate how you get it out of there. Yeah, reservoirs usually have natural gas, and this gas has pressure on it, and it's compacted, because gas will compact, gas will compact. And so when the gas forces the oil to the surface, it's called a reservoir drive, because the reservoir is providing its own mechanism for bringing things to the surface. Now, two ways gas can be present in the oil. You have solution gas, which is dissolved gas. It's mixed in with the oil. Then you have a gas cap, which is the gas floating on top of the oil and it's pushing down on it. Normal pressure of the fluid column alone generates the pressure. So, and then abnormal pressure, weight over lying rock. Now, artesian effect. When the water table is above the surface, now that's important, the artesian effect. Let's say, I think we had a picture on that. We do. Now, normal pressure of fresh water is about less than a half a pound. And when you go down in the formations with the dirt and everything, the dirt part is like 0.52 pounds psi per foot. So you go down 2 feet, you have maybe about 1 psi, a little bit more than 1 psi. But when you go in the water psi is going to be a little different. Now, abnormal pressure can come in a formation. When you see this warp, that's a syncline, and then here's an anticline. Well, when that formation or that rock got bent due to plate tectonics, then this water is putting a pressure on this oil. It's pushing because water tries to find its own level. So it's trying to level off or reach its own level. So it's pushing down. And when you tap this oil and release the valve or open the valve on the surface, this oil will come out because of the water pushing up on it, pushing it out. Then we have the Barnett Shale. I know a lot of you heard of the Barnett Shale. It's here it is, where is it? It's in West Texas, kind of West Texas, Southwest Texas. And what it is famous for is it's a big shale formation where they're doing a lot of fracking and getting a lot of oil and gas out of the ground. So I hope you learned a lot from this second part. We still have a few more things to cover, but I think this is going to give you a good foundation so that you can do well in this class. If you have any questions, please don't hesitate to let me know. And there will be a test on both of these slides, and if you look at them, you'll get a pretty good idea of what's on it. Thanks a lot. Bye.